What if I told you that a black hole could pass straight through the Earth, and most of us wouldn't even notice it? No fire, no explosion, no Hollywood destruction, just silence. Because the universe doesn't kill you the way movies show it. It does something far more unsettling. It lets physics do the job. Imagine for a moment that everything you think you know about black holes comes not from physics, but from movies. In those stories, black holes are cosmic monsters endlessly hungry, tearing through space like vacuum cleaners, swallowing stars, planets, and entire galaxies just because they can. It's a compelling image, dramatic and terrifying, and completely wrong. In reality, a black hole is not defined by what it eats, but by how much mass it has and how tightly that mass is packed. Strip away the Hollywood soundtrack and special effects, and what you're left with is an object that obeys the same laws of gravity as everything else in the universe. Here's the first mental reset we needed. Gravity does not care whether an object is a glowing star, a cold rock, or a black hole. Gravity only cares about mass and distance. That's it. If you could magically replace the sun with a black hole of exactly the same mass, Earth would not suddenly be pulled inward and destroyed. It would continue orbiting in almost the same way it does now. Seasons would still happen. The year would still be a year. The catastrophe wouldn't come from being sucked in. It would come from the absence of sunlight. That single fact alone tells you something profound. Black holes are not special because they are violent. They are special because they are extreme. The reason black holes seem so frightening is not because their gravity is stronger than anything else of the same mass, but because you can get very, very close to them. With a star like the sun, you can't approach its center because the star itself is in the way, radiating heat and light, pushing you back. With a black hole, there is no solid surface. There's no glowing warning sign. You can approach incredibly close before gravity becomes overwhelming. That's where the danger lies, not in some universal suction effect, but in proximity. Now take that corrected understanding and apply it to a more unsettling question. What if a black hole actually passed through Earth? Not orbited it, not came near it, passed directly through it like a cosmic needle threading a planetary bead. The first thing to understand is that this would have to be a relatively small black hole on a cosmic scale, something with the mass of a star, not the supermassive kind sitting in the centers of galaxies. A supermassive black hole wouldn't politely pass through Earth. It would rewrite the solar system before getting anywhere close. But a stellar mass black hole, that's a different story. If such a black hole were traveling through space and happened to intersect Earth's path, it wouldn't stop. Black holes don't slow down to savor their meals. They move according to momentum and gravity like everything else. It would enter Earth on one side, travel through the planet's interior, and exit out the other side, all in a matter of minutes. There would be no giant explosion at the surface, no planet-sized fireball visible from space. In fact, from a distance, Earth might look almost unchanged. That's the part that feels most disturbing, because our instincts tell us that something so extreme should produce something equally dramatic, but the drama wouldn't be on the surface, it would be inside. As the black hole passes through Earth, its gravity would tug on nearby matter. Not all at once, not uniformly, but differentially. The side of Earth closer to the black hole would feel a slightly stronger pull than the side farther away. This difference in gravitational pull is called a tidal force, and tidal forces over black holes truly reveal their power. It's the same basic physics that causes ocean tides due to the moon, but scaled up to a level that geology has never experienced. As the black hole moves through the planet, Earth's material, solid rock, molten metal, everything would be stretched and squeezed along the path of the black hole's trajectory. Matter would be pulled inward toward the black hole as it approaches, then flung outward as it departs. This process has an almost whimsical name, spaghettification, but there is nothing whimsical about what it does. Rock behaves less like rock and more like taffy under these conditions, elongate, and compressing in ways that permanently alter the planet's internal structure. What's important here is scale. The black hole itself might be no larger than a city, or even smaller, yet the gravitational disruption it causes would extend thousands of kilometers. Earth's core, metal, and crust would all feel the effect. Shock waves would propagate through the planet not just once, but repeatedly as the disturbed material settles and resettles. Think of striking a bell. You don't just hear a single sound. The bell vibrates, rings, and slowly quiets over time. Earth would do the same, except the ringing would be in the form of earthquakes that travel around the globe. These wouldn't be ordinary earthquakes measured on familiar scales. They would be global in reach, capable of triggering volcanic activity, shifting tectonic plates, and rearranging stress patterns that took hundreds of millions of years to form. Even if the planet didn't crack apart, it would be wounded in a deep, internal way. The geological stability we take for granted would be gone. Mountains wouldn't crumble instantly, but the forces that hold them in place would be compromised. And here's another counterintuitive detail: the black hole would not consume Earth. Despite passing directly through the planet, it would only swallow a relatively small amount of matter. Space, even inside Earth, is mostly empty at the atomic level. Atoms are tiny nuclei surrounded by vast regions of nothing. The black hole would interact gravitationally with a lot of material, but physically collide with very little of it. The Earth would lose some mass, yes, but not enough to simply vanish or collapse into the black hole. This brings us to a deeper realization about how the universe works. Catastrophe doesn't always announce itself with spectacle. Sometimes it arrives quietly, governed by equations, indifferent to whether or not anyone is watching. A black hole passing through Earth would not be the cinematic end of the world we imagine, but something arguably more unsettling, a subtle, invisible event that leaves behind long-term consequences rather than instant annihilation. And in that sense, the scenario forces us to confront how poorly our intuitions match reality at cosmic scales. We are evolved to understand falling rocks and moving animals, not objects that bend space-time and pass through planets. The universe operates with a calm ruthlessness, following rules that don't care about fear, hope, or storytelling. When we replace myths with physics, we don't lose wonder. We gain something better, an appreciation for how strange, precise, and quietly powerful reality truly is. Once the black hole has passed through Earth, the real story begins to unfold, and it unfolds not in a single dramatic moment, but in a slow, planet-wide response to an internal shock unlike anything Earth has ever experienced. The damage is not localized to a crater or a single fault line. It is distributed, echoing through the planet's interior like vibrations traveling through a struck gong. This is where our intuition fails us again, because we tend to associate destruction with explosions and surface damage. What actually happens here is far more subtle and far more consequential. Inside Earth, layers that normally behave in predictable ways are suddenly forced into unfamiliar roles. The solid inner core, the liquid outer core, the viscous mantle, and the brittle crust all respond differently to the intense tidal forces imposed by the passing black hole. As material is pulled inward toward the black hole's path and then released, it doesn't simply snap back to its original position. Energy has been injected into the system. Heat is generated, pressure gradients shift, Earth's interior is effectively stirred. And once you stir a planet, it takes a very long time to settle. One of the most immediate effects would be seismic activity on a scale that dwarfs anything recorded in human history. Earthquakes would not be confined to plate boundaries. They would propagate through regions that are normally geologically quiet, because the disturbance originates deep within the planet rather than at its surface. Waves of compression and shear would race around the globe, intersecting, reinforcing, and interfering with one another. The planet would not experience a single quake, but a sequence of them as energy reflects and refracts through different layers. The surface response to this internal chaos would be unsettling rather than spectacular. Buildings would sway, oceans would slosh, and coastlines would experience massive planet-spanning. Tsunamis generated not by a single impact, but by the collective motion of Earth's crust. These waves would not behave like ordinary tsunamis triggered by earthquakes or landslides. They would arrive from unexpected directions, overlap, and persist longer because the source of disturbance is global rather than local. At the same time, the mantle, normally flowing at a pace measured in centimeters per year, would be temporarily accelerated. This doesn't mean continents would sprint across the globe, but it does mean that stress stored over millions of years could be released in a matter of days or weeks. Volcanoes long considered dormant might awaken not because magma suddenly decided to rise, but because the pressure keeping it in place has been disrupted. New fissures could open, releasing heat and gases from deep within Earth, subtly altering the atmosphere over time. And still, Earth does not explode. This is perhaps the most counterintuitive part of the entire scenario. Despite the violence occurring beneath our feet, the planet remains gravitationally bound. its mass is largely intact. The energy involved, while enormous on human scales, is not enough to overcome the gravitational glue holding Earth together. Instead of destruction, what we get is transformation. The planet is shaken, rearranged, and left in a state that is no longer the stable Earth we evolved on. This leads us to a question that feels almost unavoidable. Would life survive? The answer depends on what we mean by survival. Life, as a phenomenon, is remarkably resilient. Bacteria thrive near deep-sea vents under crushing pressure and extreme heat. Microbial life would almost certainly persist somewhere on or within Earth, but human civilization is another matter entirely. Civilization depends on stability, predictable climates, solid ground, reliable oceans. Remove that stability, and the systems we rely on begin to unravel. The climatic consequences would not be immediate, but they would be profound. The redistribution of heat from Earth's interior could alter ocean currents, which in turn regulate global climate. Increased volcanic activity would inject ash and aerosols into the atmosphere, reflecting sunlight and cooling the planet, at least temporarily. At the same time, released greenhouse gases could push temperatures in the opposite direction over longer timescales. Climate, already a complex system, would become even more chaotic, driven by forces originating deep below the surface. What makes this scenario particularly unsettling is how little of it would be visible from space. An alien civilization observing Earth from afar might see a familiar blue planet, still intact, still orbiting its star. They would not immediately know that something extraordinary had occurred. The sign of damage would be written in seismic data, atmospheric chemistry, and long-term climate patterns, not in a shattered planetary shell. Earth would look fine even as its surface becomes increasingly hostile to complex life. This quiet aftermath challenges our instinctive definition of disaster. We tend to think of survival in binary terms, destroyed or not destroyed, but nature rarely works in binaries. It operates in gradients and probabilities. A black hole passing through Earth would not end the planet, but it would push it into a new state, one less compatible with the delicate balance that allowed advanced life to flourish. The danger lies not in instant obliteration, but in the slow erosion of the conditions we depend on. And this brings us to a deeper appreciation of the planet we inhabit. Earth is not merely a rock in space. It is a finely tuned system where geology, atmosphere, oceans, and life are interlinked in ways that took billions of years to develop. Disturb that system at its core, and the consequences ripple outward, touching everything, not because the universe is malicious, but because it is consistent. The laws of physics do not negotiate. They simply apply everywhere, all the time. In the aftermath of a black hole passing through Earth, the question that inevitably arises is whether humanity could endure such a cataclysm. Survival, in this context, is not simply a matter of avoiding immediate death. It is about whether the intricate systems that sustain civilization, agriculture, infrastructure, energy grids, communication networks could withstand the sudden upheaval of the planet's interior and the resulting environmental chaos. On a human scale, some individuals might survive the initial geological convulsion, particularly if they are in structurally sound locations or underground shelters. But the larger picture is more sobering. Cities might remain standing temporarily, but they would be fundamentally compromised. Bridges, tunnels, and high-rises are designed to withstand the kinds of stresses that occur under normal Earth conditions, not extraordinary tidal distortions and global-scale shaking induced by a black hole slicing through the planet. Electrical grids could fail, water supplies could be contaminated, and transportation networks might collapse, leaving humanity isolated in ways it has never experienced before. Survival, then, becomes less about avoiding being crushed or burned and more about navigating a dramatically altered environment where the rules we have relied on no longer hold. The planet's climate would be another formidable challenge to human endurance. The disturbance in Earth's interior could shift ocean currents, disrupt wind patterns, and trigger massive volcanic eruptions that inject ash and gases into the atmosphere. These volcanic aerosols would reflect sunlight, potentially plunging regions into a form of volcanic winter, while greenhouse gases could simultaneously warm other areas. The result would be a world where familiar seasonal patterns no longer apply, where agricultural zones shift unpredictably, and where access to fresh water could become increasingly limited. Humanity's ability to adapt would be tested not just by the immediate aftermath, but by months and years of environmental instability. Civilizations are resilient, but they depend on a degree of predictability in their surroundings, and a black hole's passage would remove that predictability entirely. The challenge of survival is as much about societal adaptation as it is about individual resilience. Perhaps the most unsettling aspect of this scenario is the invisible nature of the threat. Unlike an asteroid, which announces its presence with a streak of light across the sky, or a volcano, which may provide warnings through tremors and gas emissions, a black hole emits no visible radiation that would alert us to its approach. No sirens would sound. No telescopes would detect a looming shape unless we were already scanning the cosmos meticulously. To the naked eye, the black hole is a ghost, a manifestation of gravity alone, moving through space with no trace, except for the distortions it leaves behind in matter and energy. The invisibility of the threat forces us to reconsider what danger means on cosmic scales. Most of what can threaten us in the universe does so without warning, without intent, without malice. It simply exists, indifferent to our survival, obeying the inexorable laws of physics. This is a universe where being cautious, predictive, and observant is not just prudent. It is essential for understanding our place in reality. The concept of invisibility extends beyond the physical presence of the black hole. Even after it passes, the consequences are initially subtle. Seismic and atmospheric changes begin internally, propagating outward in ways that are measurable scientifically but not immediately perceptible to human senses. A person standing on solid ground might feel nothing at first, while oceans 1,000 kilometers away begin to oscillate in response to redistributed mass and tidal forces. Slowly, the effects accumulate, and only over hours, days, and weeks does the full scope of the disturbance become apparent. Civilization is vulnerable, not only because of the scale of the disruption, but because the warning signs are so easily missed. Our intuitions, tuned to detect immediate threats and visual cues, are almost entirely inadequate in the face of cosmic phenomena. This is why astrophysics and careful observation are indispensable. The universe operates on scales that defy human perception, and understanding it requires tools that extend our senses far beyond their natural limits. The absence of immediate drama also underscores the subtlety and precision of physical law. A black hole moving through Earth does not cause chaos out of intent, or energy released in a single explosive event. Its effects emerge from the consistent application of gravity on matter. Tidal forces stretch and squeeze, energy is redistributed, and matter reacts according to predictable equations. This is a universe that is indifferent yet lawful, and that lawfulness is what allows scientists to predict outcomes in such extreme scenarios. We can model the path of a black hole, estimate the stresses on Earth's interior, and anticipate shifts in climate and geology. The predictability does not mitigate the danger, but it allows us to intellectually grasp the scale of what occurs, which is in itself a form of survival, understanding the threat, so we can, in theory, prepare for its consequences, or at least comprehend its implications. Even in this indirect, invisible form, the consequences of the black hole's passage highlight the fragility of the systems upon which human life depends. Agriculture relies on stable weather patterns, transportation on intact infrastructure, and communication on energy networks. A single silent event disrupting the internal dynamics of the planet can cascade outward into every aspect of human existence. The initial tidal distortions propagate into earthquakes and volcanic activity, which then reshape climate and topography, ultimately affecting everything from food supply to economic systems. The challenge is that these cascading effects are nonlinear. Small changes in one area can produce outsized impacts elsewhere, making the overall picture unpredictable. In essence, humanity could survive the initial passage physically, but thriving in the altered environment would be an entirely different question. What is perhaps most profound about the invisible nature of such a threat is the perspective it offers on our place in the cosmos. Earth is not isolated, nor is it shielded from the broader universe. While life has evolved under remarkably stable conditions for billions of years, those conditions are contingent. They are a delicate balance maintained in a dynamic, often indifferent universe, a black hole, passing through is a reminder that stability is provisional and that cosmic events occur independently of human existence. This understanding can be unsettling, but it also cultivates a kind of humility. The universe does not operate with human concerns in mind. Its processes are impersonal and universal. Yet recognizing this allows us to value and protect the fragile conditions that do allow life to flourish here on Earth, emphasizing the responsibility that comes with awareness of cosmic realities. The invisible threat also brings into focus the importance of science as a predictive tool. Without careful observation, mathematical modeling, and a deep understanding of physical laws, humanity would be almost entirely blind to such dangers. It is not sufficient to rely on instinct or history. Cosmic threats operate on scales of mass, distance, and energy far beyond everyday experience. The black hole, moving silently through space, becomes a lens through which we see. The necessity of extending our perception beyond the immediate and familiar. Knowledge itself becomes a form of protection. By studying the behavior of black holes, understanding gravity, and modeling planetary responses, we gain insight that allows us to anticipate the otherwise invisible and prepare, at least intellectually, for events that are inevitable in a universe governed by immutable laws. This scenario also challenges our notions of immediacy in danger. Human experience is dominated by threats that are immediate and observable. A falling rock, a lightning strike, a hurricane on the horizon. The black hole presents a form of danger that unfolds on multiple temporal layers. Its presence may not be noticed until it is already in transit. Its effects propagate over minutes to hours, but the secondary consequences, infrastructure, collapse, climate disruption, ecological shifts extend over months and years. This layered unfolding requires a conceptual expansion of what it means to perceive and respond to threats, compelling us to think in terms not of moments but of processes and sequences. Understanding this layered nature is critical for grasping the true scale of planetary events and their impact on complex systems such as civilization. When we step back from the immediate terror of a black hole passing through Earth and consider the broader context, one of the first things to realize is just how improbably rare such an event truly is. Space is vast, almost incomprehensibly so. The distances between stars, let alone black holes, are measured in light years, with the nearest stellar neighbors separated by millions of times the distance from Earth to the Sun. Even the black holes that form from massive stars are not scattered densely through space. They are isolated objects, remnants of stellar evolution, that occupy tiny fractions of the galaxy's volume. The likelihood that one of these objects would intersect Earth's orbit is vanishingly small. In practical terms, a black hole moving through Earth is not something we expect to witness within the lifespan of human civilization, or even the lifespan of the planet itself. Yet, considering the hypothetical scenario illuminates much about the nature of cosmic events and the vulnerability of our planet. The rarity of such encounters does not diminish their significance, however. On the contrary, contemplating improbable events teaches us humility, encourages us to refine our understanding of risk on cosmic scales. Humans are evolutionarily programmed to respond to threats that are immediate, visible, and tangible. A falling rock or a predator in the grass triggers an instinctive reaction. A black hole passing through Earth, however, does none of these things. It is silent, invisible, and indifferent. This forces us to expand our conception of danger to realize that the universe operates on scales that are both vast and impersonal. The cosmos does not act with malice or intent. It merely follows the laws of physics. Events of catastrophic potential can and do occur independently of human observation or understanding, and it is through the lens of science that we gain the ability to perceive and anticipate them. The concept of invisibility is not limited to the passage of the black hole itself. It extends to the consequences that ripple through Earth long after the object has moved on. Seismic disturbances, shifts in ocean currents, disruptions to climate, and volcanic activity may unfold over weeks, months, or even years. These changes are measurable scientifically, but they are not immediately visible or dramatic in the way that movies suggest a cataclysm should be. A civilization unprepared for subtle, gradual changes could experience disruption not because the planet is destroyed, but because the systems upon which human life depends, agriculture, energy, communication, transportation are sensitive to small perturbations. Survival becomes less a matter of escaping annihilation and more a matter of adapting to a radically altered environment where incremental effects accumulate into existential challenges. Considering this, the universe presents itself not as an antagonist, but as a reminder of our own vulnerability. Earth is not immune to cosmic phenomena. It exists in a dynamic and occasionally hostile environment where stability is provisional. Life persists not because the cosmos is benevolent, but because conditions happen to fall within a narrow range that allows complexity to emerge and endure. A black hole passing through Earth illustrates how fragile these conditions are. The disruption of internal planetary dynamics, even without immediate total destruction, would test the resilience of every ecosystem, every species, and particularly human society. This awareness of fragility fosters a dual perspective at the mechanisms that sustain life, and humility in the face of forces that are fundamentally indifferent to our existence. The scenario also underscores the universality and impartiality of physical laws. A black hole moving through space does not discriminate between cities or forests, humans or microbes. It follows the same equations everywhere, in every circumstance with perfect consistency. This impersonal operation of nature contrasts sharply with our perception of danger, which is usually human-centered, narrative-driven, and emotionally charged. By observing and understanding the predictable behavior of black holes and their interaction with matter, we gain insight into a universe that is both indifferent and intelligible. Knowledge, in this sense, becomes a form of power, allowing us to anticipate and model events that are otherwise imperceptible. Yet, it is precisely the predictability of these laws that makes the thought experiment so compelling. While the odds of a black hole intersecting Earth are infinitesimal, understanding the consequences relies on applying known principles: gravity, momentum, tidal forces, thermodynamics, and fluid dynamics. The passage of a black hole, though silent and invisible, can be analyzed mathematically, simulated on supercomputers, and described with confidence in the outcomes, even when those outcomes are extraordinary. This highlights the remarkable reach of human cognition. Our minds, aided by observation, mathematics, and technology, can extend awareness across scale that would otherwise be incomprehensible, from subatomic interactions to galactic movements. It is this capacity for understanding that allows us to contemplate a near impossible event with intellectual clarity and even emotional appreciation for the cosmic drama unfolding in theory. Moreover, this awareness deepens our understanding of fragility, contingency, and the interconnectedness of systems. Earth is a complex, self-regulating system, and its stability relies on numerous interdependent processes, from tectonic plate dynamics to climate patterns and ocean circulation, disrupting one element, such as the internal mass distribution through a black hole. This passage initiates a cascade of responses throughout the system. These cascading effects are nonlinear, meaning that small shifts can amplify into massive changes elsewhere. Humanity, dependent on this finely tuned equilibrium, becomes acutely aware of its reliance on conditions that are both stable and rare. The passage of a black hole serves as an extreme illustration of how environmental stability underpins civilization, and how small disruptions, imperceptible in isolation, can propagate into global challenges. This thought experiment also illuminates the psychological dimensions of cosmic risk. Humans are remarkably poor at intuitively grasping probabilities that operate on extreme scales, while the statistical likelihood of a black hole intersecting Earth is exceedingly low. The conceptual exercise compels us to confront the limits of perception and instinct. We naturally discount risks that are remote, invisible, or abstract, yet these are precisely the risks that dominate the cosmic stage. By forcing consideration of improbable but physically plausible events, we cultivate the capacity to think critically about survival, preparedness, and the long-term stewardship of our planet. Awareness, in this context, becomes a form of defense against the indifferent mechanics of the universe. At the same time, contemplating such a scenario offers a profound sense of perspective. The universe is vast, ancient, and governed by forces far beyond human control. Within this immensity, our planet is a fragile oasis of life, and humanity's place, though significant in cultural and intellectual terms, is physically negligible. A black hole passing through Earth illustrates this vividly. From a distance, the planet might appear unchanged, orbiting its star like it always has, while internally it is profoundly altered. Civilization, ecosystems, and geology are subject to the impartial dynamics of mass and gravity. This realization challenges anthropocentric assumptions and compels a form of cosmic humility, reminding us that life persists not because of universal benevolence, but because the circumstances happen to align within narrow windows that permit complexity. Ultimately, the scenario teaches a dual lesson about the universe and ourselves. The rarity of the event underscores the vastness and relative emptiness of space, reassuring us that existential threats on cosmic scales are extraordinarily uncommon. Yet the invisible, impersonal, and far-reaching consequences demonstrate the delicate balance upon which life depends. We are reminded that survival is contingent, stability is provisional, and awareness is essential. It is not sufficient to react to threats as they appear. We must cultivate understanding, extend observation, and model the universe with rigor. For in the cosmos, danger is neither intentional nor visible, and yet it is real, governed by unyielding laws that extend across space and time. Recognizing this is not an exercise in fear, it is an exercise in clarity, an invitation to marvel at the mechanism that allow our planet to exist at all and to appreciate the extraordinary circumstances that make life possible. In studying these extreme scenarios, we are forced to confront both the fragility of our world and the remarkable human capacity to understand, and in doing so, to respond thoughtfully to a universe that is indifferent, vast, and infinitely fascinating. And so, when we step back from the mind-bending scenario of a black hole slicing through our planet, we are left with a profound understanding. The universe is neither hostile nor benevolent, it is simply vast, indifferent, and governed by immutable laws. What seems like chaos on a cosmic scale is simply the precise application of physics operating with perfect consistency. Earth, fragile and resilient at the same time, reminds us of the extraordinary conditions that allow life to flourish, and the responsibility we bear to understand, protect, and cherish this rare oasis in an immense cosmos. While the odds of such an event happening are astronomically low, imagining it stretches our minds, humbles our perspective, and deepens our appreciation for the delicate balance of our planet. Thank you all for joining me on this journey into the cosmos, for contemplating the invisible forces that shape our world, and for daring to imagine the unimaginable. Until next time, keep looking up, keep questioning, and never stop exploring.